All right, so section 3.5 deals with a cross product. So the cross product is different from the dot product in that the cross product is a vector. And recall that the dot product is a scalar. Right, so the cross product has some applications, but first look at the definition of the cross product. If you have two vectors in R3, u and v, then the cross product of u and v, defined by that, is basically the vector obtained by having the x component of the vector be that quantity, the y component be having that quantity, and the z component having that quantity. And in terms of determinant notation, you can write u cross v as a vector with x component, that's a determinant of that 2 by 2 matrix, y component that is the minus of the determinant of that 2 by 2 matrix, and the z component is the determinant of that 2 by 2 matrix. So what is the uses of the cross product? Well, we will establish this in the next few minutes. All right, so let's look at the cross product, important property of the cross product. Remember, cross product, unlike the dot product, is always a vector, and it's a vector that's got an important property. If you take the cross product between two vectors u and v, then that's a new vector, and that vector is going to have the property that it's orthogonal to both the vector u and the vector v. Okay, now we can check this by just looking at the dot product between the cross product of u and v. Firstly, with the vector u, and I mean, you can quickly go and check that. So that's going to be u1, u2, v3 minus u1, u3, v2 plus u2, u3, v1 minus u1, v3, u2, okay, and then the last one is plus u3, u1, v2 minus u3, u2, and v1. Okay, now you can see now that if you look at the first term, u1, u2, v3, so this term here cancels with that term there, okay. This term here cancels with that term there, and that term there is v2, u1, that term cancels with that term there, okay. So basically, I mean, you can easily see that that is clearly 0. Okay, now you can check the other way as well. So you can take the vector u cross v, and you can dot it with v, and you'll get the same situation there. So that's going to be v1, u2, v3 minus v1, u3, v2, okay, plus v2, u3, v1 minus v2, u1, v3, and the last one is plus v3, u1, v2, okay, plus or minus v3, u2, v1. All right, so now you can again the same story. that this term cancels with that term there. Okay. That term cancels with that term there. And this term here cancels with that term there. Okay. So basically, right. So that means that the dot product, well, sorry, it means that the cross product between two vectors is always orthogonal to both the vectors in my cross product. And that is very useful, as we will see with the next example. All right, so an application of the cross product. Let's apply it to the following example. There they ask us to find the equation of the plane that contains 3 points, P, Q, and R. All right, now the thing here that I want to use is the cross product. So yeah, I'm given these vectors here. Sorry, let me just rather do it this way. So I'm given the 3 points. Okay, I'm given those 3 points. I'm given the point 3, 0, 0, and that's the point P. I'm given the point Q, which is 1, 2, 1, and then I'm given the point R, which is 2, 0, 1. Now I want to find the plane that equation of the plane that contains those 3 points. So what I'm going to look at is I'm going to look at this vector here, which is the vector P, Q. Okay. Then I'm going to look at this vector here, and that is the vector PR. Okay, so the vector PQ we know is the vector 1 minus 3, which is minus 2, 2 minus 0, which is 2, and 1 minus 0, which is 1. Okay, and the vector PR is the vector minus 1, 0, and 1. Okay, so basically, if you take the cross product between the vectors, okay, if you take the cross product, and let's call that the vector n. If you take the cross product between PQ and PR, all right. All right, let me just fix that. I'm going to take the cross product between I'm going to take the cross product between PR first, PR, and PQ. Okay. All right, so that you can go and work that out. That is going to be the vector 0 times 1 minus 1 times 2. Okay. The second component is going to be 1 times minus 2. Okay. Minus 1 times 1. And the last component is going to be minus 1 times 2 minus 0 times minus 2. Okay, so that is going to then become the vector minus 2, minus 1, and minus 2. All right, so that is the vector. So basically, this vector here is the vector that is orthogonal to both the vectors PQ and PR. So basically, you can see it as that vector that's orthogonal. It's orthogonal to both those two vectors there. So now what I want to do is I want to answer the question. So the equation of the plane then becomes, so the equation of the plane, so the equation of the plane becomes so the equation of the plane becomes then it's the normal vector, right? So I want the plane to have a starting point there. So you're going to have the starting point x minus 3. Okay, you're going to have y minus 0. Okay, and you're going to have z minus 0 is equal to 0. And the normal vector for the plane here is going to be the vector that I worked out, which is this one here, minus 2, minus 1, and minus 2. Okay, so then simplifying after that will then give you the equation of the plane that contains the three mentioned points. All right. So that's just a neat little application of the cross product to find, given 3 points, find the plane that contains the 3 points. All right, so Theorem 3.5.1 just involves some properties of a cross product. So the relationship between dots and crosses. So again, we proved previously that both these two properties hold. In other words, the cross product of two vectors is basically a vector that's orthogonal to both the vectors in the product. Then we also have Lagrange's identity. I'm not going to look at the proof of that because it's pretty much it's a good exercise to do. To prove that the left-hand side is equal to the right-hand side, but it is pretty much just it's very similar to the proofs of these two results here. It's merely factoring everything in and comparing the left and the right-hand side. The same for the next two properties. This is known as the triple vector product, and it's the same as what you have there on the right hand side, and then also we've got the triple vector product, well, another version of the triple vector product, and that is going to be equal to that. So one can actually see here that if the operation on vectors is the cross product, then you can see that here associativity does not necessarily hold, because this is not necessarily the same as this. So remember, with matrix multiplication we had that associativity holds. So if you have matrices A, B, C, then A with B, C is still the same as A with B with C. And in the case where you have the two triple products, number D and number E, you can clearly see by comparing that U cross with V cross with W is not necessarily the same as crossing U with V and then crossing that with W. Those two expressions there on the right hand side, they are clearly not always the same. So when it comes to cross products and vectors, you'll see that the cross product associativity doesn't necessarily hold when it comes to vectors. So associativity with regards to cross products don't generally hold. Next we have Theorem 3.5.2. Cross product of two vectors, it's not commutative, so U cross V is not the same as V cross U. However, U cross V is the same as the negative of V cross U, and that can easily be verified. And then the cross product, when it comes to vector addition, then the cross product is the distributive law with respect to the cross product. So the distributive law still holds, and the distributive law on the right hand side also holds. So remember, if you go back to matrices, remember if you have a matrix A, B, and C, and you add B and C together, then remember this distributive law was true with respect to matrix addition and multiplication. So in this case, when the operation is on vectors and you're taking the cross product, then this left and right distributive laws hold. And when it comes to the scalar multiple of a cross product, it's basically the same as taking the scalar separately with each vector and taking the cross product with the other vector. Okay, so I mean scalar multiplication works very similar in a cross product. And then also if you take the cross product with a zero vector, it's always the zero vector. And if you take the cross product of a vector with itself, then it's also the zero vector. And guys, again, I'm not, like I said, not going to look at the proofs of these results, because it's a good exercise to go and do, and I can ask you something like that, but it is merely applying the cross product directly and verifying that the left-hand side is equal to the right-hand side. All right, just next we have the alternative, another form of the cross product. You can write the cross product as the determinant of this matrix. Okay. Now remember what the index I stood for. I is just the standard unit. Remember we spoke about standard unit vectors, and I is just basically it's this vector here. It's just the standard unit vector. Also, what will J be? J will be this standard unit vector. It's this standard unit vector. Right, and again, what is Z? Z is, K. What is K? K is just this standard unit vector. Okay. Now, if you take the determinant of this matrix here, then you can write U cross V as in this particular form. Okay. Right, and this is the vector. This is the vector we talked about in the beginning of the lesson, what the cross product is. Then the second definition is just the scalar triple product. We're doing this the scalar triple product because we are going to apply it very briefly in the end of this section. And the scalar triple product, you can actually verify. So what you would do is you would take a vector U, you would take V and W, and you will take the cross product, like we explained in the beginning of the lesson, and you will take the dot product of that vector with U, and that's known as the scalar triple product. Now, you can actually go and verify that the scalar triple product, if you go and write all of that out, all of that out by taking a vector U as U1, U2, U3, and you take the vector again V as V1, V2, V3, and W as W1, W2, W3, then in fact the scalar triple product is this nice little determinant of a matrix. Now we know how to work that determinant out of that 3x3 matrix. You can do that as an exercise. And you can clearly see, or easily verify that the scalar triple product is in fact the determinant of that matrix. So we're going to look at, in just a moment, we're going to look at an application for the scalar triple product. Okay, so let's look at an application of the cross product. A few more applications. So here we've got a parallelogram, and suppose that I'm interested in finding the area of this parallelogram. Now it turns out that one can use vectors to do this. Now let's take the parallelogram and let's create vectors, the vector u and v, and we look at the norm of the vector u and the norm of the vector v, because I want to find the area of this parallelogram. Now the area of a parallelogram is basically the orthogonal weight, okay, also known as the altitude, that you then multiply with the length of the base. Okay, so that is what we're interested in. So how do we use vectors to do this? Right, let's go back to Lagrange's identity. So take that identity that we talked about. We're going to use that. Okay, so basically we said we had u cross v. We take the square root of that norm, and we know that is equal to the square of that norm multiplied by the square of the norm v minus the square of u multiplied by the square of v's norm multiplied by the cosine squared of theta. Okay, now where does this expression come from? Where does that expression come from? Right, go back to our notes. Go back to this expression here. So what is this? What's that expression? What's the expression u dot v? Remember we said u dot v is the norm of u multiplied by the norm of v multiplied by the cosine of the angle between those two vectors, remember? So now going back to that, remember we took u dot v and we pretty much replaced it with the norm of u multiplied by the norm of v multiplied by the cosine of the angle between the two. Okay, so that gives me this expression. Okay, so now we can go back to finishing this up. So that then just becomes the norm of u multiplied by the norm of v, both of them squared, multiplied with 1 minus cosine of theta. And what is 1 minus cosine of theta? It is sine squared theta. So that's the norm of u squared multiplied by the norm of v squared multiplied by the sine of theta squared. All right, so from there, it implies that the norm of u cross v can be solved as the norm of u multiplied by the norm of v multiplied by the sine of the angle between the two vectors. Now go back here and you'll see there that's the angle between the two vectors. And what is this sine? Where does this sine? What exactly is this? If you look at this length, right, which is basically the altitude of the parallelogram, that is basically how do we find the length of that edge? It's basically going to be it's basically going to be the norm of V multiplied by the sine of the angle between the two, right? Okay, so this expression here, that expression is the altitude of the parallelogram, and this this expression here is basically the base. It's the base of the the length of the base of the parallelogram. So therefore, it follows that you can then basically say that U cross V is equal to the area, of the given parallelogram. Okay. Okay, this brings us to theorem 3.5.4, which if you're given two vectors in two space, u and v, and you are asked to find the area of the parallelogram determined by those two vectors, right? Then the area of that parallelogram is the determinant of this 2 by 2 matrix. Now remember, the cross product, we only work with vectors in 3 space. So what we can go and do is we can go and write u, v so that they're in 3 space. So so you can basically define u as the vector with x component u1, y component u2, and you drop the z component to 0, and you can define v as the vector in 3 space with coordinates v1, v2, and 0. So then if you look at the dot product, the cross product between u and v. Now, what is the cross product between u and v? We know that by the alternative form, it's those unit vectors I, j, k, and then it is the determinant of this matrix here, u1, u2, 0, v1, v2, 0. And we know if we go and work that determinant out, it is basically going to be the determinant of a 2 by 2 matrix, which is this matrix here, the matrix u1, u2, v1, v2. And that's going to be a scalar, and you're going to look at the scalar multiple of that vector. Okay, next up, what do we want? We want the area of the parallelogram stretched by those two vectors. We know that that's the norm of this vector. We proved this just now. So that's going to be the norm of this whole vector here, which is the determinant. Remember, the determinant in this case is just a scalar. It's just a scalar. So we apply our norm rules for vectors. Okay, so what is the norm of that? So remember, this is my scalar. So you take the absolute value of that scalar. Okay. Multiplied by the norm of k, and k is one of the standard unit vectors. So that is just then going to be, it's going to be the determinant. It's going to be the determinant of this matrix here. Okay, so that is the area of a parallelogram stretched by, or basically formed by, two vectors in two space. All right, next let's look at this object here, which is basically a parallelogram in three space. So let's say I want the volume of this object. Can I have some further applications for the cross product? And the answer is yes. So we're going to use the cross product to actually look at what the volume of this parallelogram in three space is. Right. So this the volume of this parallelogram in three space is actually given by the determinant of this matrix. Okay, now what is this matrix? This matrix is the entries of that matrix are basically entries of three vectors, u, v, and w. Now, what are these three vectors? Where do they fit into the picture? Right, so there we've got the parallelogram in three space, and we have the vectors that form that three space parallelogram. So the question is, we want to find the volume of this object. So if we look at this this object, then what we want to do is, we know the volume is going to be, so what we do is we take and rotate it and place it flat on the floor. Right? Right, and now what we want to do is we want to find the area. So we need to know what the area of the base is. Okay, so it's this area here of this colored region. Okay, that's what we want. So we want to find the area of the base, and we already know what the area of the base is. We know the area. The base is a parallelogram, and we know what the area of the base of a parallelogram is using the result we proved previously. All right, so again, if we look at the, so let's move this object here, and I want to find the base, the area of the base. Okay, so area of the base, so area, okay, so area of the base, so area of the base is basically, it's the norm of the vector v cross w. Okay, that's the parallelogram theorem that we did previously. So now we're looking at the area. Okay, so now we need to get the altitude of this object. So how do we get the altitude of this object? Okay, so we're going to use the projection theorem. So let's look at the altitude. So what is the altitude? Is basically, I'm just going to color this with yellow, and that's going to be the altitude. We want that, the height. Okay. Now you can do this pretty much. You can work out that height, which is that length there, by considering this vector here. Okay, now this whole vector, so let's just get rid of that quickly. What I want to do is, this whole vector is a vector that is orthogonal to both v and w. Right, so if you take the cross product between the vector v and w. So that's the cross product between the vector v and w. That's the vector. That is the vector that is this vector here. That's orthogonal to both the vector v and the vector w. Okay. So we know that the height, okay, is basically going to be what? It's going to be the norm of the orthogonal projection. The orthogonal projection of the vector u onto the vector v cross w. Okay, so it's orthogonal projection of u onto the vector v cross w. So essentially I want to look at, this is the vector u, and I want to orthogonally project it onto the vector v cross w. And that is going to give me this particular height here. Okay, now going further, so what is the projection of u onto v cross w? It's going to be the dot product of u with v cross w, okay? And you're going to divide that basically by the norm of v cross the norm of v cross w, right? Multiplied by the norm of u, and you're going to multiply that with the vector u, and you're going to take the norm of that. Now we know by our norm rules, we can then easily see that that is going to be the absolute value of this dot product here. This is the norm rules that I apply to a scalar multiple of a vector. So that's going to be the absolute value of the scalar multiple, okay, which is going to be that multiplied by the norm of this cross that, okay, multiplied by the norm of the actual vector, which is the vector u. All right, and from that we know that that is going to cancel with that. Okay, and so we have that then becomes it becomes the absolute value of u dot v cross w, okay, divided by the norm of the cross product between the two. Okay, so that is an expression for the height of this parallelogram in 3 space. So what is the volume? The volume is the altitude, which I just worked out, which is the height, multiplied by the area of the base. Right, so the volume is so the volume is the area of the base multiplied by the height. Okay, so that is going to be equal to, so we have this, that is the area of the, or rather it's the height that we worked out. And now we're going to take the area of the base, okay, and we're going to multiply that together there. And so basically that cancels with that. And so we've got equality there. It's the absolute value of u dot v cross w. Now, guys, this is the scalar triple product. This is the scalar triple product. So we talked about the scalar triple product a short while ago. All right, recall that we talked about this. The scalar triple product is the determinant of that matrix with the entries we talked about, U, V, and W. Okay, and we worked out the volume as the absolute value of that scalar triple product. And those two things are the same. So it shows that the volume of our parallelogram in 3 space is given by that determinant. All right, next we have theorem 3.5.5. So this theorem just tells us, let's say we've got 3 vectors with the same initial point, and we want to establish when are those 3 vectors in the same plane. So we're given vectors u, v, and w. When do these 3 vectors lie in this, with the same initial point? When do they lie in the same plane? They lie in the same plane when the scalar triple product is equal to 0, and the scalar triple product was the determinant of this matrix with those entries there. Now we know that these 3 vectors, they induce a 3-dimensional parallelogram, which is given here's just a schematic representation, and we said that is the vector W, this is the vector U, and that's the vector V. Okay, so those were those vectors we talked about. Now the question is, when will these 3 vectors lie in the same plane? Well, that will happen when geometrically, when the volume of this 3-dimensional parallelogram is 0. And that occurs when one of 2 things happen. The first thing is if the area of the base is 0. Okay, so it's the area of this the base. Okay, now when will the area of the base be 0? As an example, it'll occur, say, when V and W point in the same direction. Okay, then the area of that base will be 0. When is the other case where the area of this parallelogram, this 3-dimensional parallelogram will be 0, is when it has 0 height. And that will occur when U is in basically the vector U. If we look at this vector U, when that vector lies in this plane here. Okay, so in both those instances, we will have a parallelogram, a 3-dimensional parallelogram that will have 0 volume. Now, to see geometrically what I meant with the height being 0 is going back to the 3 vectors. What you essentially do is, in that case, is if you take the vector u, you drop it down onto the plane that is induced by these 2 vectors w and v. So there's the vector u that you drop down. Now in that case you'll see that the parallelogram that we originally, with a 3-dimensional parallelogram, is going to have obviously a height of 0. So that is an illustration of what will happen in that case. So to find out whether 3 vectors lie in the same plane, it's equivalent to looking at the volume of the 3-dimensional parallelogram and when that is actually 0. And the only way they can lie in the same plane is when that the parallelogram in 3 space, 3-dimensional parallelogram, has volume 0.